in this module we are going to learn about derivation of the height of the liquid raised inside the capillary tube. Now let's consider a capillary tube inside the beaker as shown. Now we know that as soon as we put the capillary tube inside the liquid, the water is going to rise inside the capillary tube, something as shown inside the figure. And the top surface, if you see inside the capillary tube, we have a concave surface, right? And that is nothing but the free surface of the liquid. Let h be the height of the liquid inside the capillary tube, something as shown. Now I say that due to surface tension, a surface film is formed on the water which is inside the capillary tube, which is blinking right now inside the tube if you see carefully, right? Now this is nothing but the free surface and it wants to reduce its own area. So I say that this free surface wants to reduce its size and therefore it pulls the wall of the capillary tube, and this force, let us say this is nothing but the surface tension force, that is T, something as shown inside the figure. But now class, according to Newton's third law of motion, every action has equal and opposite reaction. So that means if the free surface is trying to pull the walls of the capillary, even the walls of the capillary is going to pull the free surface in the opposite direction with equal magnitude of force. So I say that let the force provided by the capillary tube on the surface film be T, something as shown. Now let theta be the angle of contact, and because of the vertically opposite angle we see that even those angles are theta. Now the components of T along y axis is T cos theta and along x axis it is T sin theta. But if you see carefully, the T sin theta, that is the horizontal component of T, gets cancelled because it is equal in magnitude and opposite in direction in all the sides, and hence T sin theta cancels each other. But if you talk about T cos theta, all the T cos thetas are acting vertically upward direction. So I say that T cos thetas are the forces responsible for the pull of the water in the upward direction. So I say that total effect of this force along the entire circumference is T cos theta into 2 pi r. So this is the force with which the liquid is getting pulled in the upward direction, and that force is T cos theta into 2 pi r. So I say that force T cos theta into 2 pi r pulls the water in the upward direction, and hence the water starts moving in the upward direction. But class, if you look at the diagram carefully, as we know that as the water moves upwards, its weight increases inside the capillary tube, and that weight is acting vertically downward. So the upward force is T cos theta into 2 pi r, and the downward force is weight of the water. And the water will stop moving in the upward direction only when the upward force and the downward forces are balanced by each other. So I say that T cos theta into 2 pi r is equal to W, where W is nothing but the weight of the liquid inside the capillary tube. Now we know that weight is equal to mg, mass can be written as volume into density, and volume can be written as area into height. So I say that area of the capillary tube is nothing but pi r square into height into rho into g. Now both of the r gets cancelled, so we have 2t cos theta is equal to rh rho g. So we have h is equal to 2t cos theta upon r rho g. So this is nothing but the expression of the height of the liquid raised inside the capillary tube above the normal level. Okay class, so I say that this is the height to which the liquid rises inside the capillary tube. Okay.